The World Summit of Integrative Medicine 2015 presents Nassim Haramein. Nassim Haramein is a pioneer of a new approach to quantum gravity and continual developments in unified field theory. As the founder of the Resonance Project, Nassim has been delivering lectures and seminars on unification theory for over 20 years worldwide.
Hi everybody, this is Nassim Haramein, and I've been doing physics for some 25 years, and I came up with a unified view of physics, but more importantly a unified view of our universe and the way we interact with it. So my presentation today is called The Connected Universe, and it has to do with some of the new physics that are emerging in the world right now that is showing that our universe may not be this cold, disconnected, entropic universe that is so often described in physical theory, but actually that our universe is a lively, connected universe in which negentropy and organization and complexity emerge, us being evidence of it. And so you can start with two different views of the universe. You can start with the view that it's disconnected, that anything that you study here may not be happening over there, and that it has no impact what you're doing here because it's not connected to everything else. Or you can come to a different conclusion that the universe is highly connected, that everything is talking, and that when you do something here, it has an influence somewhere else. And if you look at nature and you were to conclude from nature which one would be the correct approach to describe our universe, I think that most people would agree that at least from the study of nature, you would come to conclude that there's some kind of deep interconnectedness, that all systems are bounded together, that ecosystems influence each other, and that everything is in a state of very fine balance that makes it all work, and that the evidence of complexity and highly coherent systems, like for instance, the 100 trillion cell that makes up the human being, don't come together under random function, which mathematically doesn't add up, but actually come together as a result of highly coherent, interconnected structures that have feedback embedded in them. So this might sound really complex, but let me just say that if we there's more and more evidence that supports the concept that the universe is highly connected, and but the problem is that our current physics are disconnected. Literally, our physics are separated, are broken in some ways, meaning that we have physics for the very big and physics for the very small. So let me go to the next slide. What we're trying to find is a unified view, and currently our physics are not unified, they're deunified. We have two sets of physics. We have a set of physics that's called cosmology and astrophysics, and it deals with the big stuff. Typically it's described as, that stuff is described with Einstein field equations that describe the gravitational effects on objects onto each other, like galaxies, stars, even cosmology, like universes and stuff, and planets and all this stuff. And then we have a set of physics that is called quantum theory or quantum physics, that deals with the small stuff, that deals with molecules all the way down to atoms and subatomic particles and all this stuff. And these two sets of physics don't agree. One is Einstein field equations that describe gravity at the cosmological level, and the other one is quantum physics, which describes subatomic and particle physics. And the two don't agree because one describes the universe as this smooth continuum, and the other one describes the universe as these little packets of energy. Quantum physics describe the universe in these linear packets of energy that are like integer based, so the two views don't agree at all. And this has been the case for almost 100 years. And in general, it was kind of accepted that way. When I started in physics, it was remarkable because I would go to physics conference and I would say, people would ask me what I'm working on. I'd say, I'm working on unifying physics. And they'd ask, why? Why do you want to unify physics? And I'd be, well, because the universe probably only has one set of rules that rules at all the scales. But it had been somehow accepted that there was two different models on how things were done, and we used this model for the big stuff and this model for the small stuff. The thing is that the big stuff is made out of the small stuff, so of course there must be like one set of physics that rolls it all. And certainly Einstein thought so, and he worked till literally the day he died. I mean, hours before he died, he was working on these equations, trying to find a solution to unify the field. And, I think that if Einstein would have had the tools we have today, and the data that we get from these tools, from Hubble and many space telescope and some of the stuff we're getting from quantum experiment, that he would have solved this unification problem. But what I did is I looked at both sides, both equations, and when I drilled down, so like when I, add to the slide the astrophysical body, like stellar objects, and then on the other side, the atomic structure of quantum theory, of quantum physics, and then, black holes in cosmology, and then on the quantum side, the nuclei of atoms. And so basically when you drill down, I was looking for like a point that would connect the two, like if there was some part of physics somewhere where I could see was existing or existent in both sides. And I got to this thing called singularities or black holes. And I realized that when black holes were predicted by Einstein field equation, it predicted that in the center of a black hole, there'd be a point of infinite density called a singularity. And I found out that on the quantum side, at the foundation of quantum physics, at the base of the structure of quantum physics, there was this field of energy that predicted these equations that predicted that space is not empty, but that every point in space is infinitely dense with energy. And in both cases, then, these infinity singularity things were occurring. And, and I thought, well, maybe that's the point that connects the two. That point is described usually as a Planck entity, meaning there's a very specific distance called the Planck length that defines that singularity. And so if I click on again, you can see that both relate to this Planck length that's 10 to the minus 33 centimeters. That's present both in the center of a black hole, or at least in black hole theory, or in gravitational theory of Einstein, and at the quantum level. And I thought maybe that's the point, literally, that connects the two. And you know, if you so basically if you this very very tiny singularity is in the vacuum structure of quantum physics, meaning that in the space of quantum physics, this energy in these little Planck points is present everywhere. And if you were to ask, well, what connects everything in the universe, if you were trying to find a universal connective agent, if you were to look for something that connects everything, that would be space. Because space is present everywhere. It's present between galaxies, it's present between stars, it's present between planets, it's present between atoms and molecules, like the densest molecule on Earth. If you were to grow it so that it be one of the atoms in the in a carbon molecule or a diamond molecule, which is extremely dense, if you were to grow one of those atoms so that it's an orange, the other orange in the same molecule would be 2 football fields away. So there's a lot of space in between atoms inside molecules. And there's a lot of space inside the atom itself. So if I click on, you will see that the atom is made out of 99.9999999% space, which is like remarkable, because atomic structure, the material world around us, seems to be very solid, seems to be very, dense, but actually it's mostly made out of space. So basically what we call the material world is like the space itself oscillating, making this denser region that we call matter around us. And so I came to conclude early on that maybe it's not matter that defines the space, it's not the objects that defines the space, but it's the space that defines the objects. Maybe it's the other way around. Maybe we should study the 99.99999% more than we study the 0.00001 of a percent. And that would really kind of turn things around. And it's hard for people to believe that space is not empty, that it's full of this energy, that it's full of these Plancks. And I'll explain in a minute why it's not obvious to us that space is full. But throughout the ages, there's been some of the greatest thinkers in the world that have said some things about space, about so-called empty space, that are quite startling. And they've been ignored, although they were some of the most important scientists we've had in history. For instance, John Archibald Wheeler, here we can see him on the picture, walking around with Einstein and some of his colleagues, said, no point is more central than this, that empty space is not empty. It is the seat of some of the most violent physics. So, clearly, and certainly Wheeler was probably one of the greatest physicists, along with Einstein. But these guys didn't say things like that lightly. And Wheeler was encouraging us to, examine deeply the possibility that space is actually the source of the physics that we observe in our reality every day, that we call matter. David Bohm was another incredible physicist. He said, space is not empty, it's full. The universe is not separate from this cosmic sea of energy. So, again, another very important physicist telling us to look at space if we're trying to understand matter, if we're trying to understand the universe. Einstein himself said physical objects are not in space, but these objects are spatially extended. That means that an object is not like, you know, just sitting in the space separated from the space, but an object is an extension of the space manifesting itself. Basically, that an object is denser regions of space. And he continues to say, in this way, the concept of empty space loses its meaning. That was Einstein. So, a long time ago, many physicists, some of the greatest we have in history, told us that we should look at space, or what we call empty space, to understand the reality of our world better. But in general, that has been ignored. Why were these physicists saying this? I mean, of course, people like Wheeler and Bohm and Einstein didn't just say these things with no supporting evidence to come to these conclusions. It's because when the study of quantum physics, and especially quantum field theory, were extrapolated, these studies told us that space itself is full of energy, that the structure of space is not void of energy, but actually that space-time at the quantum level is incredibly dense with energy. And in fact, John Wheeler described these, very specific energy levels to be so high that actually space at the quantum level would be riddled with little wormholes that connects particles together. And eventually, finally, eventually, just recently, there's been work by Leonard Susskind and other physicists that have described a direct relationship, and this is something I've been discussing for a very long time, that particle entanglement, the fact that we're able to measure in laboratory that two particles, no matter how far they are from each other, if they're entangled, they behave as if they were one. And so basically, if you scatter, electrons, or if you scatter photons onto a particle, like a carbon particle, two photons will go flying out. And if you change the polarization angle of one photon, the other one will change instantaneously as well to the new angle that you put on the one photon. And it doesn't matter how far they are from each other in the universe, they will change instantaneously. And we're discovering now that the reason why this is happening is because particles are entangled in such a way that they are, linked with these micro wormholes that are in the structure of space at the quantum level because the energies are so high. So this is very remarkable. It's taken a long time. Those papers from Maldicina and Susskind were just published in 2013, where John Wheeler already 15, 20 or 20 some years ago, or even earlier, some 30 years ago, was already on to the possibility that space at the quantum level is actually riddled with wormhole connecting the whole thing. And he had come to the conclusion that maybe there was only one electron in the whole universe, and it was just going around really fast, instantaneously, in fact, around all the atoms. And it looked like there's a whole bunch, but there was only one. So This is very different than the picture we have of our universe, where things are completely separated. In this case, everything seems to be highly connected to these wormhole structures. Well, okay, these wormholes are Planck length wormhole, and we just talked about the Planck length a little bit, but I want to give you an idea how, because people say, well, if space is full of this energy, space is full of these wormhole strings and all this, why am I not experiencing it directly? Well, it has to do with scales. First of all, people think of space as empty, but it's hardly that. Space is not empty at all. For instance, the electromagnetic energy in space is always present, meaning that, for instance, in the room you're at right now, unless you're sitting in a Faraday cage, but even if you were, there would still be some of that. There's ultraviolet, there's infrared, there's radio waves, if you turn on your radio set, it will pick up on those radio waves and you'll hear the music. That stuff is in the space all around you. There's radiation from the sun, there's this radiation from the galactic center, which is galactic cosmic rays that are hitting our solar system. I mean, there's radiation coming from the Big Bang, and so on. So, there's radiation all the time, and you don't necessarily experience it directly. You think of the space as empty, but certainly the Planck distance radiation level or electromagnetic fluctuation. So those Plancks are basically little spinners. They're little angular momentum oscillators, and if you were to try to get a sense of size, let me give you kind of an example of how small the Planck is. So if we took the dome of the Vatican that we have on this slide, and the dome of the Vatican is approximately 42 meters. So it's pretty big. In it, you look like a little person, very small. So we pasted on the slide Susan, because Susan is really dedicated, so she climbed on top of the Vatican. Not really, but we put her there. So now you get a sense of Susan's relative to the Vatican dome. And those are the relatively correct scale. So there's Susan there, if I click on. And Susan is made up of 100 trillion cells. And each one of those cells, so that's a lot of cells. So cells are already small. But if you think about it, each one of those cells are made up of approximately 100 trillion atoms. So atoms are extremely small. And so if I made an atom the size of the Vatican dome, then the nuclei in the middle of that atom would be approximately, the little proton would be approximately the size of the head of the pin of that Susan is holding there. So actually, if you're holding a pin in the middle of the Vatican, you're already small relative to the Vatican dome. If you're holding a pin in the middle, the head of that pin is the nucleus of an atom. And that's why an atom is made out of 99.99999% space, because basically you have an electron cloud, an electron shell, and then a little nucleus in the middle, and the rest is just space. Well, if I made, so nucleons or protons are very teeny little things. So that gives you an idea of scale. Well, if I made one of those Planck distance, 10 to the minus 33 centimeters, if I made that so that it was a grain of sand. So basically, a grain of sand is really small relative to the Earth. And so as I click on, you can see that, like, if I make a Planck the size of a grain of sand, of course, a grain of sand is not even visible from, space, if you're looking at the Earth, so it's teeny relative to the Earth. And then if I click on, the Earth is kind of teeny relative to the sun. Here's the Earth flying by, right by the sun. It's approximately correct scales. And, well, if a Planck was the size of a grain of sand, then the diameter of a proton, which is a teeny object usually, would be the size from our sun to approximately Alpha Centauri, which is 40 trillion kilometers approximately. So, that's how small the Planck field is. That's how small the Planck electromagnetic fluctuations are. And of course, that is really, that isn't anything you're going to experience directly. So of course, you don't necessarily know it's there. You don't necessarily experience it. And so it's kind of remained hidden from humans until, more recent times, where people have been starting to think about the Planck and the Planck field at the quantum level and wonder if they can start, extracting energy from it, or if, this field of information is actually the source of reality or not. So it all leads to this concept that space is not empty but full of these Planck fluctuations, these Planck's little spinners. And if you calculate how many of these little Planck spinners there is in a centimeter cube of space, you will find 10 to the 93 grams per centimeter cube is present in a centimeter cube of space, because each little Planck is a little mass, is a little energy, it's a little oscillator. So you can calculate this, it's about a 10 to the minus 5 gram mass for each Planck. You calculate how many Plancks there is in a centimeter cube. I think it's in the upwards of 10 to the 99 something. So there's a lot of Plancks in a centimeter cube. And you multiply that by the Planck mass, which is 10 to minus 5 gram, to get the amount of Planck mass, or the Planck energy, there is in a centimeter cube. And that's 10 to the 93 grams per centimeter cube. It's huge. It's 10 with 93 zeros. It's a very large number. How large is that? Well, if I took all the stars in our universe and I stuck them into a centimeter cube of space, that centimeter cube would have a density of 10 to the 55 grams per centimeter cube. So you would actually not be anywhere close to the density of the vacuum. You would be, still 39 orders of magnitude off the density of the vacuum. So, a centimeter cube with the whole universe in it is nowhere close to the density of the vacuum energy that I'm talking about. So it's a non-trivial thing. And it's been ignored largely because the number is so large that many physicists felt like, it wasn't something that could be explored. I started to think about it a long time ago. And I started to think that maybe, just maybe, if you were to make a scaling law, you could show that space divides itself in very specific, size ratios that would, show a linear progression on a scale. So Dr. Rauscher and I plotted the points from the Planck length on one side all the way to the universal size, and found out that like they line up very nicely, and that all the points in between, like galactic centers and quasars and stars and even atoms, line up on that line very, very well. The only thing is that many of the other points, including the universe and the Planck length, can be considered black holes, but the atom is typically not thought as being a black hole. And so why was the atom lining up on that linear scale so nicely when it's not a black hole? And because, you know, the rest of the stuff obeys the condition of a Schwarzschild solution, a Schwarzschild black hole. Well, you know, which is the solution to Einstein's equation. So I had to examine the atom in detail. This vacuum energy is is not a figment of our imagination, but actually there is a measurement in the mainstream experiment in laboratories that actually showed that two plates can be pushed together by the vacuum itself, meaning if you get plates close enough together, you can eliminate some of the longer wavelengths of the vacuum energy and have only the short wavelengths in the middle, which makes a gradient so that the plates get pushed literally by the structure of space. They get pushed together by space itself. And now we have a dynamical Casimir effect where the plates are actually being oscillated by semiconductors, that they replace the plate by semiconductors and they oscillate them very fast. And what they are doing is basically pumping the vacuum energy and getting photons to emerge from the vacuum energy, showing that actually you can extract some of the energy that's in the vacuum. So this vacuum energy is not just at the quantum level, but at the cosmological level as well. When we looked at the way the evolution of the universe happened, we thought that it was like a balloon expanding. That's the current model for the expansion of the universe. And we have like galaxies glued to the balloon as the universe expands. This is really remarkable, but because we measure that. But the thing is that who's blowing into the balloon? Who's the guy blowing the balloon? If we draw the rest of the guy, we find that in order for the balloon to expand, the lungs must contract. And so basically, the guy that's blowing the balloon is the vacuum or the space inside the balloon that's being expanded. And we know that's present at the cosmological level. We call it dark energy. And it is supposedly the effect of this vacuum fluctuation expanding our universe at the universal size level. So it's not just confined to the vacuum, to the quantum world. It's actually being measured in the cosmological world as well. So it's really there. It's not like a trivial thing. It's not just a result of, theoretical physical theory, but it's actually present in the world, for real, and it can be measured in laboratory, and it's being measured at the cosmological level as well. So what I did is that I tried to figure out why we didn't think the atom was a black hole. And, because it has, subatomic particle, like the proton, the nuclei of an atom, has all sorts of attributes that resemble attributes that a black hole has. And so, I start to examine, what we think about the proton or the nuclei of an atom. And it appeared to me right away, of course, and to many other physicists, would be that the black hole, the proton mass is just not high enough to be called a black hole. But then I realized that we weren't considering the vacuum energy inside one proton. So I started to calculate that. I calculated the volume of a proton, and then I calculated how many little Plancks would fit in there to see if the mass of all the Plancks together inside the little proton would be enough to make the proton a black hole. And when I calculated this, something remarkable happened, because the number that came out was 10 to the 55 grams, which just happens to be the mass of the universe. That is, all the little Planck energy, the little Planck masses inside one proton, inside the volume of one proton, which is a very small volume. It's 10 to the minus 39 centimeters. All the little Plancks in there make up the mass of the universe. So if all the protons were connected through these little wormholes that connect the whole grid, then you would expect that you could find all the information of all the other protons in the universe present in one proton. That told me that the concept of a holographic universe was absolutely correct. And so, but I had to somehow explain how the proton had such a high mass, and we weren't actually measuring it, because we measured 10 to minus 24. And so I started on my adventure, and I knew, and it took me 5 or 6 years to find that solution. I knew that something was like really critical about that calculation that showed that there is the mass of the universe inside one proton in terms of information. And I thought maybe this energy, this information is actually, shared across scales from the wormhole connectiveness or the wormhole network, but that we would only see the localized effect, meaning that there's in order to understand the proton, we would have to consider that the proton mass is actually an influence of all the other protons on one proton. And I started to think that maybe this surface of the proton and the surface of black holes in general were maybe holographically imprinted with all these Plancks. A little bit like the holographic principle that's already in mainstream physics. So I actually made the little Planck spheres, and I plastered it on the surface of a black hole. I picked a black hole that's well known, Cygnus X1, and I plastered the little Planck all over that surface, and then I calculated how many there was there. And then I did the same thing for the inside. I packed the little Plancks inside the black hole, and I calculated how many Plancks there was. And the result was, I called the surface Plancks eta, and the internal volume Plancks R, and I did R over eta, the ratio between the inside and the surface, because I thought maybe the surface is like what's restricting us from being able to see all of the energy and all the mass that's present. That like maybe the event horizon is this barrier that the information has to move through in order to reach us. And that's why we only see a very small percentage of what's there. So I multiplied that ratio, the volume Plancks to the surface Planck. I divided that to get a ratio or a relationship, and then I multiplied that number by m sub L, or by the mass of a Planck. And the result was really amazing, because the answer was 1.683354 multiplied by 10 to the 34, which is the exact mass of that black hole. So it actually worked correctly and exactly. And basically what I had found was a new solution to Einstein field equation. A solution where, you know, instead of thinking of space-time producing gravity by curving, I was able to show that you could get the same result for black hole, but actually showing that space-time is pixelated with all these little Plancks. You can think of it as each Planck being a little bit of information, and that these bits were restricted by the surface where the volume is connected to everything else. And you know, that surface restricting the information in the volume was the key to understanding the mass of an object, because it worked exactly right. It worked like a charm. I was so surprised. But then I had to apply this to the quantum world. But before I did so, I found the algebra for this geometric solution, and it was beautiful. Meaning that, you know, a geometric solution like that one is beautiful because geometry is incredible and it gives you nice visuals to understand what the physics you're writing. But it's not complete until you do the algebra of that solution to actually understand its reduction, its mathematical reduction into a formula. And so, because like if you do the ratio of the surface by volume, you gotta calculate the volume, you gotta calculate how many Plancks go on the surface, how many Plancks go on the volume, and divide the two and all this stuff. But I find out that there's an elegant solution when you derive the geometry and, you know, reduce it, you end up with 2 times the Planck length multiplied by the Planck by the mass of the object divided by the Planck length will give you the radius of the object. So it's actually a beautiful solution. And so I thought, well, you know, if basically I had described gravity with quantum objects, the Planck, so maybe, you know, the Planck's density, maybe, you know, since these Plancks are quantum objects, maybe my equation works at the quantum size as well to predict the mass or the radius of a proton. And so I calculated for the proton, and I calculated the number of Plancks on the surface, the number of Plancks on the inside, and the two, you know, one over the other multiplied by the Planck mass to get the energy or the geometry, the energy of that system, gave the exact mass of the proton. So actually it worked extremely well. And you know, I was so surprised because I was dealing with huge number. The number of Plancks inside the volume of a proton is still 10 to the 60th, which is a huge number. And the number of Plancks on the surface is 10 to the 40th, which is a big number as well. So all these things are very, large numbers. And to think that from such large numbers, you could get a ratio that would go and nail the mass of an object that's in the region of 10 to the minus 24 grams and nail it very good. The solution was within 0.0012 of the codata value, of the value that's measured in laboratory for the proton. So I had found a quantum solution to not only black holes, a quantum solution to gravity at the level of black holes, but all the way down to the proton. And so unifying gravity with the atomic level, it was remarkable. And again, the solution said even more topologically, the solution was saying something about the geometry of how these little Planck spheres were interacting with each other, because the equation is wrong or comes up with the wrong answer if the little Planck spheres are tiled so that they're adjacent to each other or tangential to each other. Because if they're tangential like that, that means that there's a space in between, and that won't add up. Like if you tile them like that on the surface and on the interior and count them, you'll get the wrong answer as far as getting, the correct amount to get the mass of the proton or the mass of a black hole. So the answer is only correct when the space is removed from the center between the Planck. So it's best not to visualize the Planck as little billiard balls. They're electromagnetic little spinners, and they can interact just like when you throw rocks on the surface of a pond. The rings can interact together and create these interference patterns, which are typical of holographic systems. And funny enough, this geometry is found all around the world and is thought of as the flower of life. And under the paw of the Sphinx, or the food dogs, here, at the Forbidden City, is where the food dogs or the Sphinx guards the knowledge. And right underneath its paw is this very pattern, over top of a sphere, which is the exact solution to gravity as I'm showing. So basically, I had found a solution to gravity that said something different than Einstein. It said that actually the surface of water, imagine that you're in a bath and you pull the plug and the water is going down the drain and you have a rubber ducky. And, the rubber ducky in the vicinity of the drain is going to orbit, and it's going to look like it's attracted to the drain because the surface is curved towards the center. And this is what Einstein described. He said that gravity was like the curvature of space-time. But the fact is that the rubber ducky is orbiting because the water molecules are all co-moving in that region of the drain, and it's entraining the rest of the material around it to do the same and to appear attracted to the drain. So it's really kind of different picture, and it's more fundamental, because what this equation is saying is that space-time is just like in your bath, can be like these Plancks can be kind of disorganized or more chaotic in certain regions, but where there's matter is because these Plancks are co-moving and spinning in a coherent matter in that region, like a little vortex in the structure of space-time. and we call that an atom, or we call that a galactic center, or a galactic black hole, or a quasar, or whatever. So, it's a completely different picture of the universe that develops from this. And it eventually led to, because you can actually start to understand the structure of space-time at a completely different level. And here I have a little animation, a little movie we've made with the help of, a wonderful animator in England that donated his time to help us visualize this. Because if you take every sphere in the flower of life structure, if you take every little Planck sphere, you can actually reduce them to little tetrahedron. And you can look at the way the tetrahedrons interact with each other to create that spin component. And so here's the little animation we made. So it starts with these, this is called an isotropic vector metric. And so this, you can think of like each tetrahedron there being, the center of a sphere, and you can see how it claps and unclaps. And as a result, you get spin, counterspin on the structure. And here we're gonna like grow the field to the next level up. So now you have, a larger structure, this was just like one seed. Now we have like the whole thing. And you can see that you can find in this way of, this is what Buckminster Fuller called the jitterbug, the way the geometry claps and unclaps. And you can see here the Star of David in 3D, or the Merkaba, there's all sorts of names for that, emerge from that. But all the Platonic solids emerge from this movement. All the solids, all the geometry we see in nature emerge. Here it's shown with the spheres and around the tetrahedron with the little Plancks. And then what we're gonna do is we're gonna grow the field again to a larger size. Here we're growing it on one side only, just to show you. And I find this really interesting at this level. It looks a lot like the fiber of a heart beating. The ventricula of the heart beating and pushing the blood across the whole body. And here we're basically building the field to give an idea. Basically, that's the information moving in and out of the vacuum across the membrane of the black hole, like the information moving in and the information moving out as it torques together. It's fairly complex, and of course the computers cannot render that level of density because the Planck is so small. If you actually looked at the proton, you would not see the Plancks, and they're billions of times smaller than the protons, so it would appear smooth. And basically, this is the error we've made. We thought that space-time was smooth, but it's actually not smooth at the quantum level, at the very, very fine level, even past quantum, like all the way down to the Planck. At the Planck level, it's granulate. And it's the granulate Plancks moving together that produce the effect that we call matter. When the Plancks are moving in coherent region of space, we call it a proton or an atom or a star, a galaxy, whatever. So, again, this geometry reduced to, algebra. And now when I wrote that algebra, I realized that if I change the equation around, I could, instead of just predicting the mass of the proton, which is well known, I could plug in the mass of the proton that we measure in laboratory and predict what its radius should be. And because the radius of the proton is a big, difficult thing to measure, and I thought maybe I can predict what it should be exactly, and the experiments can confirm it. So I predicted in my paper that I published on December 21st of 2000, or 20th or 21st of 2012. And my equation said that the proton radius should be exactly 0.841236 multiplied by 10 to the minus 13 centimeters. And that was some 4% smaller than is predicted by the mainstream standard model. But after I published 3 months later or 2 months later, in January of 2013, an experiment that I didn't know about was being conducted at an accelerator in Switzerland in order to measure the radius of the proton more precisely than it had ever been measured before. And the result was very, very close to my prediction. In fact, my prediction was now within 0.00036 of the radius of the proton that was measured. And more importantly, my prediction is inside the margin of error of that experiment. So that means the experiment may be off by 0.00036. And my prediction, did I say one too many zeros? I think it's 0.00036, yeah. And maybe the experiment is getting close to my theoretical result. And my theoretical result is actually the accurate result. Whatever the case may be, this prediction is now and still stands to this day as the most precise prediction of the radius of the proton, which is critical to all the physics we do. And the standard model is off by 4%. And that's what upset the world of physics for a very long time now. That's why you see it on the cover of magazine in the past few years. For instance, on the New Scientist, teeny particle, big problem. The Hubble proton is nothing like we expected. No kidding. It's it's not a little billiard ball. It's actually an agglomeration of Planck fluctuation, of electromagnetic fluctuations. The Scientific American in February of 2014, the proton problem. Could scientists be, this is about the radius of the proton, could scientists be seeing signs of a whole new realm of physics? Absolutely. This problem with the radius of the proton is pointing, as my theory demonstrates, directly to the fact that the proton is actually an agglomeration of little Plancks. Well, in the last few months, we presented a paper to the scientific community in which we saying that actually the little wormhole network that connects through the Planck oscillators on the surface of the proton may be like a neural net that acts just like a brain, and that acts just like your nervous system, the spinal column, and the brain, and that the brain is actually just like an antenna, a fractal antenna. And we know the science of fractal antennas. We use them in cell phones and so on, where an antenna goes smaller and smaller and smaller so it can get all of the wavelengths and be much more effective. And so the brain acts a lot like that, and that consciousness is not actually a thing that's manufactured from the brain inside of you, but actually consciousness may be the result of your brain tapping into this field of information that's all around us and that makes up all of our reality. And so it's a completely different thing than what we see or what we think of as our brain manufacturing this epiphenomenon that we call consciousness. But actually, consciousness is the information that's permeating everything through this Planck field, and the brain is tuned into it. And it's tuned in through these fractal antennas that we call microtubules. And I can't get into too many details in this presentation, but here you can see the fractal nature of this network. For instance, here we have the fibers of the brain cells, a picture of those, and then a picture of the very large structures in the universe, those superclusters that make these filaments and so on. And it looks just the same. And then the same thing with the rendering of the Planck field by supercomputers, the simulation of what these fluctuation looks just like those neural network that we have in the brain. And so basically what we're saying is that the brain acts just like, and your nervous system, your whole body basically is like a bio-oscillator, like a crystal radio set. And you're tuned in, and if the crystal radio set is your body, if your antenna is your body, then your heart or your state of emotion is the dial that tunes that antenna, because we know that your state of emotion changes the biorhythm of your body, the chemicals that are flowing through it. So basically, your state of emotion tunes the antenna, that and other things like, your nutrition and all these other factors. But when you tune the antenna just right, you could have access to an incredible amount of information because you're connected through all of the protons that you're made of. And that's really kind of remarkable to think about, because that means that you have access to some of the most profound information in the universe about anything in the universe. And this might be why people can remote view things, because they have access to the information of what's over there. That might be why people can remote heal each other and so on. All of a sudden, many phenomena that appear completely irrational and very esoteric may be actually because of this interconnectivity of this vacuum structure that connects all things. And now we might have actual mechanical understanding and physical understanding on how all of these very, apparently strange phenomena that reside in the field of science and so on, that these things are actually part of the way things work in the universe. And I think it's non-trivial to mention that a radio set circuit, as the brain we believe is, obeys the same mathematical basis because it has nonlinear functions as a black hole. So like a simple RLC circuit, a resonant sync circuit that's found in any radio set obeys the same mathematical condition as a black hole. So, there's many devices that are coming out now that are being found, like this one, that are interacting directly with the vacuum. This one is called the EM drive. And basically it shows that if you put certain microwaves inside a can that's tighter on one end and wider on the other, a little cone, you will get a gradient difference in there, and without expelling any material, the whole thing is shut and nothing is coming out of it. This thing will start moving and producing thrust in space, and it's literally pushing against the quantum vacuum fluctuation. And this, this knowledge leads to gravity control. For instance, in Finland now, physicists have been spinning a superconductive disk, and they throw electrons on it using a Van Graph device, more sophisticated, but something along those lines. And it creates a gravitational beam that they can measure, the effect, kilometers away. And remarkably, the the electrons that are moving through the beam are propagating across the beam from from the time of emission to about 1.5 kilometers away at like 64 times the speed of light. So what I'm talking to you about has very specific engineering and technological developments that are not generations from now. It's not like your grandson that's going to be able to use this energy in the vacuum to propel their ship and so on. This is occurring very, very quickly, and we're going to, transform our world very fundamentally as a result. If we can extract 1/10 of a billionth of a percent of the energy that's in a centimeter cube of space in terms of Planck energy, we could run the planet for thousands of years. It will change our world fundamentally, and it's on its way. So, of course, at the Resonance Project, and personally, I have developed technological devices which are being patented and experimented on, and so on, that will have an impact on the gravitational field. Gravity control is one of the most important things. At this point in our history, we have to learn to fly, and we have to do it differently than burning fossil fuel. And we have to learn how to extract energy from a different source than either nuclear power or sun or wind and all this, because all of these are not sustainable over a long period of time. So this change is fundamental. It's on its way, and it has a positive impact on life too, because we're made out of the same stuff, because our cells organize most likely because of this field of energy. When you create devices that creates high level of coherency in that field of energy, then any life that's around it benefits from it. So we've done tests on plants by bringing the plants close to the devices. In this case, it's a little crystal that's being charged by our technology. And you can see that where the crystal is, grass grows greener, stronger, faster. It's remarkable result. If I click on, you can see, on the left there, very high density, high energy, very green grass. On the other side, at the same time, without the crystal underneath it, the grass looks sparse and is not growing as fast and is not as vibrant. You can find that in experiments after experiments. We verified the effect many times over. So this implies that we will be able to create superhumans at one point that are able to live much longer and so on. That we can have a very important impact even on just the vitality of a person and so on. And all these plant experiments support that this is a technology that has positive effects on life. So to conclude, what does this all mean is that we are on the verge of a breakthrough in our civilization. We will no longer be bound to the surface of our planet, and I can't stress how important that is. We have to learn to fly. Planetary systems are not stable places, not stable environments. One little asteroid, one comet coming too close, and our planet could fry. And it actually is remarkable that we're still here talking about it, but I wouldn't push our luck. We have to learn how to control gravity, and we have to learn to become galactic, what I call universal being that lives in the universe, and that are no longer bounded to one planet. And like that, we can have infinite amount of resources and so on, and the whole concept of scarcity can go away. Another thing that this means is most of our current environmental challenge will be resolved as a result, of course, when you can go off planet, when you can go orbit Jupiter for the weekend, when you can go and get material from the asteroid belt and so on in a very easily manner. All of a sudden our planet will regain its natural state, and especially if we're not directly living on it anymore, and will return to its state of garden. We will have access to almost infinite amount of energy anywhere we are in the universe. And so this is gonna change our world fundamentally. As much as it changed our world when we learned to control the electromagnetic field to power all of our devices, the lights and the computers you're watching this on and everything else. Now, as we learn to control the gravitational field, everything is going to change again, and it's going to change for the better. So we have all this information at the Resonance Academy as well. So you guys at Quantum University, some of you, it's part of your curriculum to do the course on the foundation. This is a delegate course. It's very in-depth, and all of the references are there, and all of the media is there for you to study all this information and come to your own conclusion. Everybody that's taken the course so far have been delighted. People are reporting incredible changes in their life as a result of it. So I encourage you to take it no matter what. And so thank you so much, everybody, for listening to this presentation. It's a delight to be present with you all at Quantum University. Continue your great work and your great studies. And until next time, may the vacuum be with you. Thank you, everybody. Have a wonderful time wherever you are.